Dear students, today we'll see what do we mean by Norton's theorem. And in this theorem, we will see what is the statement of the theorem and how to solve an example by using this theorem. So let's start with the topic Norton's theorem. So here we have the topic as Norton's theorem. Now first we will see the statement of this theorem. Now the statement of Norton's theorem says that Norton's theorem states that it is possible to simplify any linear circuit to an equivalent circuit with just a single current source and a parallel resistance connected to a load. That means here, if you are having any complex circuit, if you are having a complex circuit, any complex circuit which is connected to load, now this complex circuit can be replaced by a current source in parallel with a resistance. Okay, now this will become the circuit, and to this circuit you can attach your load, whatever you had earlier. Okay, so here this was your load circuit. Now this is the equivalent, and this is your load circuit here. So you can see the complex circuit is substituted by a current source and a resistance in parallel. This is what Norton's theorem says. Now we can see the statement in other form also. Any linear circuit containing several energy sources and resistances can be replaced by a single constant current generator in parallel with a single resistor. The same meaning of Norton's theorem. Then we'll see now how we are going to solve this. Now here, say for example, you are having this circuit. Now in this circuit, this is the resistance R1, this is resistance R3, which are a part of the circuit. This is your load resistance R2, which is say in between terminals A and B. And this is the voltage source, one voltage source, and this is another voltage source. Now the full circuit except the load should be converted into a current source in parallel with the resistance. That is what the Norton's theorem says. So except this load, except whatever you are having here, except this, the other two resistors and two voltage sources should be converted as a current source in parallel with a resistance. And then you can have a load resistance R2. Okay. So you should have a current source in parallel with a resistance. This will be equivalent to the circuit. And then you can have a load resistance R2, whatever was there in the main circuit. If you reduce like this is according to the Norton's theorem. So here you can see Norton's equivalent circuit. We have shown a current source which is called as Norton's current source. This is the Norton's current source. Then there is a Norton's resistance which is in parallel with that source, and this becomes your equivalent circuit. This is your equivalent circuit. The complex circuit is converted to a simple equivalent circuit. Then you can connect your load resistance, and afterwards you can measure the load current and other things. So this is how Norton's equivalent theorem helps us to reduce a complex network and to solve or to do network analysis. So let's see the steps by which we are going to solve a circuit using Norton's theorem. So the first step is remove the load resistor RL or component concerned. Find RS by shorting all voltage sources or by opening circuiting all the current sources. You have to open circuit all the current sources and short circuit all the voltage sources. Third one, find IS by placing a shorting link on the output terminals A, B. Fourth is find the current flowing through the load resistor RL. Okay, now here what does this mean is if we are having a circuit like this, say this is your circuit where you are having a resistances R1, R2 and R3. Okay, so here is your R1, here is your R2 and here is your R3, and this is the voltage source. Now whatever voltage you get across terminals A and B, this voltage will be called as VAB. Okay, now this is the voltage across terminals A and B, and the effective resistance from here R will be taken as this resistance R2. This will be in series with the parallel combination of these two resistances. So here you can see R is R2 in series with parallel combination of R1 and R3. Now this is how you get R. So the Norton current I, that is the short circuit current I, whatever is going to flow from here, can be obtained by dividing the open circuit voltage VAB by R. If you take VAB by R, you will get the value of I, and that I you can use as a Norton's current I. Okay, and that effective resistance R you can use as Norton's resistance R. This is how you can solve a Norton's theorem. Means you can use a Norton's theorem to solve a circuit. So here you can see the VAB, that is voltage across A and B, is given as, so here on top we have given the expression for VAB. So here you can see VAB is equal to V1 upon R1 plus R3, which is the current, multiplied by resistance. So here VAB is nothing but V1 upon R1 plus R3, which will give you the current, multiplied by this R3, which will give you the voltage. So voltage across this is VAB, and that is what VAB shown here. Okay, so here we have shown the VAB. Now that VAB divided by the equivalent resistance. Equivalent resistance is something what you are going to see from here. So here if you see, R2 will be in series with the parallel combination of these two resistances. So that is what is shown here. R2 is in series with the parallel combination of R1, R3, that will give you R. So here you can see the current I, that is short circuit current I, or the Norton's current I, is given as the open source voltage VAB upon the effective resistance R. Okay, and that is how you can build up this circuit for Norton's equivalent. You can have that current as current source and the resistance as equivalent resistance, and then you can have these terminals AB across which you can put the load. So this is how the main circuit is converted into a reduced circuit by using Norton's theorem. Now here one more example we'll take here so that we can understand. Now let's have a voltage source here as shown. This is the voltage source Vs. Vs will be your voltage source, and then you have a resistance R1 here, you have resistance R2 here, you have resistance R3 here, and this is the load resistance, and this is the current flowing through the load resistance. Now for this circuit we have to find out what is the short circuit current which is going to flow here when you remove the load and short circuit it, and then we should also find out what is the equivalent resistance when you see from here. Okay, so two things we have to find out. So first we'll find out the short circuit current. So here the load or our resistance we have shorted now, and we want to find out this short circuit current. Now this short circuit current can be found out by the voltage which is developed across this R3 divided by the effective resistance. Okay, so what is the voltage developed across R3? This voltage developed across R3 is the current which is flowing in this multiplied by R3. That means the current which is flowing is Vs upon R1 plus R3 multiplied by R3 will give you the voltage. Okay. Now this voltage divided by the equivalent resistor R, that will give you the current which is Isc. Okay. So this voltage divided by equivalent current R will give you the Isc, that is short circuit current, which can be used as Norton current afterwards. Okay. So here then the effective resistance is what, if you see from here, then this resistance will be in series with the parallel combination of these two resistances, R1 and R3. Okay, so there you can get it as R int, or the effective resistance, is equal to R2 plus R1 R3 upon R1 plus R3. Okay, so here you can see R int is equal to R2 plus R1 R3 upon R1 plus R3. So we have got effective resistance and we have got the short circuit current. So that short circuit current can be used as a value for the, or the magnitude for the current source. So here you can see this is the short circuit current used as a magnitude for the current source, and the effective resistance is used in parallel with that current source, and this is nothing but your Norton's equivalent circuit. Norton equivalent circuit. Okay, then across this circuit, whatever load was there in the main circuit, that you can put here, and through that load you can calculate what is IL by taking the current source and the equivalent resistance. So here load current IL also can be calculated. So here you can see IL will be nothing but the short circuit current, that is a Norton's current, multiplied by the resistance. Norton's resistance will give you voltage. This will give you voltage upon the resistance Rn plus RL will give you the load current IL. So in the end you can calculate the load current IL, but the main step was how we reduced the main circuit by using a Norton circuit to a current source in parallel with a resistance. Okay, thank you students.